You have thus far covered different kinds of polygons, right? We've had those and we've discussed about lines and angles, and now what we're going to do, since we've covered all of the kinds of polygons that we would have, is we're going to look at some of the characteristics of the insides of those polygons. So, this is a reminder. A polygon is a closed planar figure made up of 3 or more sides. What are the names of some of the polygons we've had so far? What was the first one? Quadrilateral, that's the name of one, sure. And that had how many sides? 4. 4 sides. What else do we have? Triangle, right? 3 sides. Triangle. What else did you have? Pardon me? Well, that's a kind of triangle. 5 sides. Did we have that yet? That might be the next lesson. No, that's properties of circles. Yeah, you're right. Okay, so then we had the different kinds of quadrilaterals. We had parallelogram, rhombus, rectangle, square. There are other ones though, right? There's something called a pentagon. The pentagon has 5 sides. There's something called a hexagon. And a hexagon has 6 sides. And then there's something called a hepta, H-E-P-T-A, heptagon. It has 7 sides. There's something called an octagon, 8 sides, nonagon, 9 sides, decagon, 10 sides. So the other ones were hepta, and they all end in gon. Hepta, octa, I always want to put it out. Octa, nona, and deca. And they all end in gon. So hepta, 7 sides. Octa, 8 sides. Nonagon, 9 sides. Decagon, 10 sides. Okay. Who wants to take a wild guess as what we call something with 10 or more, something greater than 10 sides, like 11 sides? Does anybody know the name of that one? It is similar to polygon, yes. Something with 11 sides is called an 11gon. I'm not making that up. That's actually what we call it, because somebody at some point along the way said, you know, I'm tired of coming up with all these names. They had something better to do, like watch paint dry. 12-sided is called a 12gon. 20-sided is called a 20gon. So the only ones with specific names are 3 through 10. Triangle, and then the different kinds of quadrilaterals. Pentagon, hexagon, heptagon, octagon, nonagon, decagon. Alright, all of those different kinds of gons, polygons, can be split into 2 different categories, convex and concave. The ones you are used to looking at are convex polygons. They go like this. That is a bad drawing of a convex hexagon. It's 6-sided. Everything is outward. There's nothing inward. A concave polygon caves in. That's where it gets the name. Here's an example of a concave quadrilateral. So quadrilateral, 4-sided. That is a concave polygon. This is a concave quadrilateral. So we need some kind of test. How do we know if it's convex or concave? We need some kind of test. Here is the test. If you can take a line and start inside the polygon, go outside, and then come back inside with one line segment, it's concave. Now watch what I'm going to do. I start inside, I go outside, then I come back inside. Because part of that polygon caves in. Somebody want to try and do it up here with the convex one? Start inside, go outside, and then come back inside with one line segment. Now I can do that with two line segments. Watch. 1, 2. I can do it with two line segments, but that's not the test. The test is one line segment. Nobody brave enough to try? Well, that's good, because it's impossible. So you... What, here? Yeah, that's why I said it was a bad drawing. Which is just an assumption in this class. If I draw it, it's going to be bad. So, convex, it's the one you're used to looking at. It's the regular looking one. Concave, caves in. Alright, let's look at these and classify each by the number of sides and state whether it is convex or concave. Should be a space here. Alright, how many sides does this one have? 4, so it makes it a quadrilateral. Can't call it anything other than that because there's no parallel sides. It's just a quadrilateral. How about this one? 1, 2, 3, 4, 5, 6. Six-sided is hexagon. How about that one? And what kind of hexagon is this? Convex or concave? Convex. This is a convex hexagon. Let's be a little more specific. This is what? Decagon. Good. Very 10-sided. That's the first thing I like to do. I like to figure out, well, what is the name of it? And then I go back and figure out convex or concave. This one, convex or concave? Concave, because you can use the one line and go out, and back in. So it is concave. And how about that one? It's not a very good drawing, but it's technically not closed, but it's close. Well, let's count the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonagon. What kind of nonagon? Convex. So that's part of what we're doing today. You are going to determine what kind of polygon it is. You're going to tell me convex or concave, and then you're going to count the number of sides and tell me what that is. Now, the concave one, look to see it if it's cave in. The examples in your textbooks are rather specific. Alright, another property we have with polygons are called diagonals. Those are lines inside the polygon, and it is a line segment that joins two vertices, but it's not a side, so it's not on the outside. Like this right here, I know it joins two vertices, but that's an outside edge of that polygon, so it is not a diagonal. The diagonal's all right here. Alright, so when we talk about diagonals, it only refers to one of the two kinds of polygons, concave or convex. If you say convex, yeah, you're right. Convex. Concave polygons, you lose stuff. So from here on out, the kind of properties we're going to talk about only refer to convex polygons. We'll not talk about concave now because they cave in, because they go in, that they lose all the properties. Alright, so what kind of polygon do I have right here? And since they're all convex, we just have to come up with the name for... That is a pentagon. 5-sided, this is a pentagon. So a pentagon has 5 sides. How many diagonals does it have? 2. 5 sides, 2 diagonals. Okay? What do I have there? 1, 2, 3, 4. Hexagon, right. So it has how many sides? 6 sides. How many diagonals does it have? 3. How about this one here? So what is the name of it? Octagon. Octagon. It has 8 sides. How many diagonals? 5 diagonals. Anybody notice a pattern here? Five, 2, 6, 3, 8, 5. Anybody see a pattern? Yeah, there's a difference of 3, right? There's always 3 more sides than there are diagonals, correct? And it has to work that way. It will always be that way. And we really don't use the diagonals so much, except that the diagonals, when I draw them in there, they form something. Now, don't look at the outside so much, but look inside this pentagon. Look inside this octagon. What do you see inside there? What shapes would those be? Those would all be triangles, wouldn't they? And that's what we're going to use, because triangles are kind of really useful, aren't they? Do we know a bunch of things about triangles? How many degrees are in every triangle, no matter what it looks like? 180 degrees, right? Might be useful. So we're going to try and ignore this for now. We have 5 sides. How many triangles do I have formed by those 2 diagonals? 3. Four triangles here. How many here? 1, 2, 3, 4, 5, 6. 6 triangles here. All right, this last one. What is it? It's quadrilateral. It's a rectangle. Would I be wrong to say that if I call that a quadrilateral? No. But usually we give it its most specific name, and I wouldn't be wrong, I just wouldn't be the most correct I could be. All right, it's a rectangle. How many triangles are there? 2. Now we want to see a pattern. Is there a pattern now? Look at the relationship between the number of sides and the number of triangles. Always 2 fewer triangles than sides, right? So if I give you the number of sides being n, you could always figure out with even looking at it how many triangles are inside of it, correct? If you have a 10-sided, if you have a decagon, how many triangles would be inside? 8. If you have a 20-gon, you'd have 18. If you had a 100-gon, you'd have 98. Now, we might use that because we know a lot about triangles. And a lot of geometry is taking a look at something we have and saying, how can I change this so I can make it look like a triangle or a circle? Because we know lots about triangles and circles. This is why. If we want to know the number of degrees total in any polygon, so if we take all the angles and add them up, we use those triangles. The angle sum of a polygon, the sum, the word sum is missing there. The sum of the interior angles of a polygon with n sides is n minus 2 times 180. What does this n minus 2 represent? Yeah, the number of triangles inside the polygon. That's what the n minus 2 represents. This tells you how many triangles inside. Why is the 180 there? Yeah, there's 180 degrees in a triangle, right? So if I go back to this pentagon, I know there are 3 triangles in here. I can do 3 times 180, right? 540. So I know in any pentagon there are 540 degrees from all the angles. If I took them and add them all up, this one plus this one plus this one plus this one, they have to equal 540 degrees. And I got that because there are 3 triangles, 180 degrees in each triangle, 3 times 180. Down here, I'd have 180 times what? 1, 2, 3, 4, 5, 6. That's 600, and 480 is 1,080 degrees. So I know in an octagon there are 1,080 degrees. Now should we bother memorizing another formula? What would be the advantage of that? Yeah, what it does is it saves time. If let's say you got this as a problem. Find the sum of the angles of a 25 gon. Who's going to want to draw that? No, I'm not. Not when I can just take and do this, plug this in for n, the 25, and do 25 minus 2 times 180. That's 23 times 180. The first part I can do in my head. 23 times 180 equals 4,140 degrees. 4,140 degrees. Now that's a lot faster than having to draw a 25 gon, I assure you. It would not be a lot of fun to draw all 25 sides and then draw all the diagonals in there and then count the number of triangles. This is much faster. So what does n represent? How many sides? Take that, subtract 2 times 180. Well, the subtraction you could do in your head. If it's 10, 10 minus 2 is 8 times 180, whatever. 800 and 640, 1,440 degrees. If you have a 12 gon, that's even better. 12 minus 2 is 10. 10 times 180 is 1,800 degrees. So that gives you the total number of degrees. That's what the first formula does. This one gives you total number of degrees in the polygon, because it's the sum of all of them. This one, the next one, gives you the angle measure of a regular polygon. Now, what does regular mean? A regular polygon. Have we had that definition yet? A regular polygon is a polygon where all sides are congruent. So the Pentagon that you're used to seeing the picture of that building, that's a regular pentagon. Well, the word regular means something. It means all the sides and angles are congruent. They're all the same. If all the sides are the same, all the angles have to be the same. So what do we call a regular triangle? It's got a special name. You said it earlier in class. That's right. An equilateral triangle is a regular triangle. We usually don't mention the term regular triangle because it has its own special name. What do we call a regular quadrilateral? It also has a special name, its own name. What quadrilateral has 4 sides? Square, right. All right. And after that, then there's regular pentagon, because we call a 5-sided figure a pentagon. We have a regular hexagon, regular octagon, regular nonagon, regular heptagon. All right, so let's look at the formula. So we know what a regular polygon is now. Let's look at this formula. Does this formula look familiar? Part of it? What does this look like? Ignore the n. Yeah, it looks like that one, isn't it? Isn't it the same as that? It is. The top part of that. So what are we finding in the top part of this formula? How many degrees are in the entire regular polygon? And then if I divide it by n, what does it do? It breaks the number of degrees down by the number of angles. N is still the number of sides, but the number of sides in a polygon and the number of angles in a polygon is the same. So all of these that you will be given today, we're just going to assume they're regular polygons. If you're asked to find the measure of an interior angle, we are going to assume it's a regular polygon. Otherwise, that would just be cruel. You would not be able to do it. I won't do that to you. So if we want to find the angle measure of a regular polygon, an angle measure. So this is for the measure of one angle. One angle in a regular polygon, since they're all the same. This one, the top one, we can use whether it's a regular polygon or not, because we're just finding the total number of degrees, so it doesn't really matter. All right. Somebody give me a regular polygon. Jeremy? Pick a number. An octagon. All right. Of a regular octagon, your stop sign, correct? Now we'll know how many degrees are in each one of those angles, not that you care. But now we can figure it out. Octagon has 8 sides. 8 minus 2 times 180 divided by 8. 8 minus 2 is 6. 6 times 180 is 600, and 480 is 1,080 divided by 8. It's 135 degrees. So in your stop sign, which is a regular octagon, there's 135 degrees in each angle. So it's what kind of angle? Obtuse, yeah. It's an obtuse angle. If you get above a quadrilateral, they're all obtuse. Pentagon, hexagon on up, they're all obtuse angles. You want to get some really big angles. Technically speaking, I mean, you could create something that has 1,000 sides, but at some point, I don't know, drafts persons, you could probably figure out at some point how many sided figure you could make. I mean, theoretically speaking, you could keep going, but at some point the line segments would be so small it would look more like a circle. Right? Where you were doing that today in lab? All right, mess around a little more, see what you can get. I'll give you some bonus points for it. All right? Let Mr. White know you're doing it. He'll jump on it. All right. What other one do we have? Well, Pentagon is the only one, is the first one where they're going to have obtuse angles. So let's figure out what, in a regular pentagon, how much each angle is. So a pentagon has 5 sides. So my n is going to be 5. 5 minus, oops. 5 minus 2 times 180 divided by 5. Common mistake made when students are doing this, they'll forget to divide by 5. You should not get a large number in the hundreds or a few hundreds or thousands. If you do that, you forgot to divide by the n at the end. So 5 minus 2 is 3. 3 times 180 is 540 divided by 5, 108 degrees. So the pentagon is the first one that has obtuse angles. A regular pentagon, each angle is 108 degrees. So let's find the sum of some of these. Decagon, I think did we do that one? First thing you need to recognize is which formula am I using. Please remind me tomorrow to get you your formula sheets. I have formula sheets for everybody. Has all the formulas you'll need, including these two. So decagon, 10 sides. We need to figure out what we're looking to find. If we're looking to find the sum of the angles, are we looking to find all of them or just one? That's the first thing you need to figure out, because that'll determine which formula you're going to use. This one is for the sum of the angles, all of them together. This one is when you're looking to find just one angle. So if we're looking to find the sum of the interior angles, is it one or all of them? All of them. So decagon, how many sides? 10. 10 minus 2 times 180. 10 minus 2 is 8. 8 times 180, that's 1,440 degrees. See how simple that was? You could do the subtraction in your head to look at the number of sides, subtract 2, and then just whatever that number is times 180. Why am I always multiplying by 180? 180 degrees in a triangle. What we have found when we multiply by 2 are the number of triangles inside that polygon. How about a 16gon? 16 minus 2 times 180. That's 14 times 180, which I'm not sure what it is off the top of my head. 2,520 degrees. 2,520. Triangle. What's the sum of all the angle measures in a triangle? 180, right? I mean, that's like a trick question. I mean, will the formula work for this? It sure will. 3 minus 2 is 1. 1 times 180, 180. Triangle, 180 degrees. And a 12gon, 12 minus 2, which is 10, times 180, 1,800. So if it looks for the sum, that's all of the angles together. The other one we're looking for is find the measure of an interior angle, which means that's where I'm looking for just the one. So I'm going to use this formula right here. Decagon has 10 sides, so that's 10. Whoa. (10 minus 2) times 180 divided by 10. 10 minus 2 is 8. 8 times 180 divided by 10. That's what, 800, 1440 divided by 10. It's 144 degrees. So a decagon and a regular decagon, each angle is 144 degrees. How about that one? Do I need the words? No. What do I put into the formula? 5 minus 2 is 3, right? Times 180 divided by 5. 5 minus 2 is 3, and I think we just did this one. There we did, 108 degrees. All right, of course you know there's some kind of analytical geometry in this, which means we're going to apply some algebra. In hexagon A, B, C, D, E, F, the measure of angle A equals the measure of angle B equals 10x degrees. C and D, angle C and D equal 3x plus 8 degrees. The measure of angle E is 7x minus 22, and the measure of angle F is 8x minus 12. Find the sum of the angle measures of the hexagon. Do I need any of this to do this? No. This is that first formula. This is this right here. All I need to do is know the number of sides. So it's a hexagon. So a hexagon is 6 minus 2 times 180 degrees. To find all the angle measures, you only need to know one. Or no, the only thing you need to know is the number of sides. That's 4 times 180, which is 720 degrees. Is this a regular polygon? Can I use the second formula? Is this a regular polygon? Are all the angle measures the same? No. So can I use the second formula? No. But what do I know about all these together? If I put them all together, they what? They equal 720, because there's 720 degrees in every hexagon. So whether they are all the same or not, I know if I add those all up, which would be 10x plus 10x, because there's two of them, A and B, and then C and D plus 3x plus 8 plus 3x plus 8 plus 7x minus 22 plus 8x minus 12 has to equal 720. Can I solve for x? I'm what? 2 steps away from solving. 2? 4 steps away from solving for x. This problem is not as bad as it looks. I'm going to add my like terms. 10 and 10 is 20, 23, 26, 33, 41. 41x. 8 plus 8 is 16. 16 minus 22 is negative 6. Minus 12 is negative 18. Now I'm 2 steps away. Add 18. That's the opposite of subtracting 18. 41x equals 738. Sure hope that divides nicely. 738 divided by 41. Oh, it does good. So I divide by 41, and I get x equals 18. So if x equals 18, I can now plug in and figure out what each angle is. The measure of angle A and the measure of angle B is both 10 times x. So that's 10 times 18. Each one of those are 180 degrees. C and D are 3 times x plus 8. So measure of angle C and the measure of angle D equals 3 times 18 plus 8. 3 times 18, that's 30, and 24 is 54, plus 8 is 62 degrees. So each one of those are 62 degrees. The measure of angle E, running out of room, equals 7 times 18 minus 22. 7 times 18, 70 and 56, 126 minus 22 is 104 degrees. And then finally the measure of angle F, 8 times 18 minus 12. It's 80, and 64 is 144 minus 12. 132 degrees. Are those all right? Sure. What if I made a mistake? Can I check it? Yeah, just add them all up. 132 plus 104 plus 62 plus 62 plus 180 plus 180. 720 degrees, so they're right. So what I did is I just took the information I knew, which is what geometry is, and then finding the other parts. 224 and 225, 1 to 30 all.